Okay, so now we are going to discuss the selected clinical calculations. First, we have the heparin dosing calculations. So, what is a heparin and how it is used? Heparin, or a heparin sodium injectable, is a heterogeneous group of a straight chain anionic mucopolysaccharides called glucosaminoglycans that has an anticoagulant properties used to prevent clot formation. Okay, so for example, we have venous thrombosis, pulmonary embolism, coagulopathies, and coronary artery clots. So when you talk about clots, it means to say that we are talking about blood clot. Okay, so there is a coagulation of your red blood cells in your blood. Okay, there is a formation of clot in your veins. So we have venous thrombosis, and then pulmonary embolism, coagulopathies, and coronary artery clots. Okay, so what is the effect of your heparin? So the effect of heparin is to lyse the red blood cells. Okay, meaning to say, iyan pala na yun ang blood clotting. So the effect of our heparin is an anticoagulant. Okay, so when you talk about anti, meaning um, there is a contradiction to our coagulation of our blood. Okay, so iyang ipalanay ang atong blood clotting. So dapat we have to control also the dosing of our heparin. It's because remember the effect of our heparin is an anticoagulant, or it has an anticoagulant property. So if masubraan ra pud ninyo og hatag ang patient, then what will be the effect? There will be the common side effect is easy bleeding and bruising. Okay? Remember again, it is an anticoagulant, so iyang palanayon ang blood clots. Okay? But if masubraan, then there will be bleeding. Okay? So that's why it is important for you to control the heparin dosing. So common side effects of heparin are easy bleeding and bruising, pain, redness, warmth, irritation, or skin changes where the medicine was injected, itching of your feet, or bruising colored skin, thrombocytopenia, heparin-induced thrombocytopenia or HIT, and heparin-induced thrombocytopenia and thrombosis or HITT are serious side effects of heparin. That's why to prevent these side effects or the thrombocytopenia, then we have to control the dosing of our heparin. Why do we need to monitor heparin dosing? Laboratory monitoring is widely recommended to measure the anticoagulant effect or unfractionated heparin and to adjust the dose to maintain level of target therapeutic range. Okay, so you have there the anticoagulant effect must be monitored. Okay, kay kung masobraan, then there will be bleeding. The most widely used laboratory assay for monitoring unfractionated heparin therapy is the activated partial thromboplastin time or APTT, a fixed therapeutic range for the APTT of 1.5 to 2.5 times the to control the value has become widely accepted, but the evidence supporting the range is weak and the clinical validity of using the APTT for predicting thromboprotic or bleeding events is questionable. The APTT test is also affected by numerous pre-analytic and analytic variables that are unrelated to the anticoagulant effect of unfractionated heparin, further eroding its potential value for monitoring unfractionated heparin treatment. Unfractionated heparin dose appears to be more important than the APTT in predicting the clinical efficacy. Despite serious limitations, the reliance on the APTT is likely to continue because of its ready availability and familiarity of the clinicians with the test. The focus of the clinicians who manage unfractionated heparin therapy should be to ensure that the adequate starting dose of unfractionated heparin is used and the APTT method is standardized. Further research efforts should be directed toward developing method to improve standardization of the APTT assay for the monitoring of unfractionated heparin. Direct measures of the concentration of unfractionated heparin in the blood are attractive because these assays are not affected by many of the biologic variables that interfere with the APTT, and many may be suitable for automation. However, currently available unfractionated heparin assays are much more expensive than the APTT and are now widely available, and their validity has not been adequately assessed in the clinical outcome study. Okay, so you have APTT. Example calculations of our heparin dosing. Okay, the problem is an intravenous infusion contained 20,000 units of heparin sodium in 1,000 ml of D5W. The rate of infusion was set at 1,600 units per hour for 160 pounds patient. Calculate A. The concentration of heparin sodium in the infusion in units per ml. B. Length of time the infusion would run in hours. And C. The dose of heparin sodium administered to the patient on amount in kilogram in minute basis. Okay, so first you are going to compute again the letter A, the concentration of heparin sodium in the infusion in units per ml. Remember that we are going to get units per ml. So in the problem, where do you see the units? So we have 20,000 units heparin sodium. Okay, some of the um, mga doses of drugs are measured by units. So first example here we have heparin. So we have 20,000 units. So you are given a 20,000 units of heparin sodium, and then the desired unit is units per ml. So now it has been said that we are going to get um, the concentration in the infusion set at in units per ml. Okay, so you have there 1000 ml, so 20,000 units over 1000 ml is equal to 20 units per ml. Okay, remember that an intravenous infusion contained 20,000 units of heparin sodium in 1000 ml of D5W. Okay, so that's why we have to get 20,000 units over 1000 ml. So our answer would be 20 units per ml. That is for letter A. For letter B, length of time the infusion would run in hours. Okay, so where do you see hours in the problem? So you have there the rate of infusion was set at 1,600 units per hour. Okay, so since you have your 20,000 units in general of the intravenous infusion, so 'di ba, naamantay 20,000 units of heparin sodium in 1,000 ml. So we are going to use again the 20,000 units. And then we have to use now the units per hour. So we have 1,600. So to cancel these units, we have to write one in the numerator and one in the denominator. So you are going to cancel the unit. Okay, so 20,000 units over 1,600 units per hour. What is left? Cancel units. Then what is left is hours. So our answer would be 12.5 hours. Okay, so that will be your answer for letter B. Now we are going to do letter C, the dose of the heparin sodium administered to the patient on amount in kilogram per minute basis. Given you already have 160 pounds, so you're going to convert these to kilograms, which is 72.7 kilograms. So your 12.5 hours is converted to 750 minutes. Remember that the desired unit is amount in kilogram per minute. So you have to convert the pounds to kilogram and then hours to minutes. So your answer for letter B is 12.5 hours, so we have to convert that to minutes. Okay, so remember that we still have to use the 20,000 units in general. So 20,000 units over 750, which is your minutes, then what is our answer would be? This would be this would be minutes. Okay, this would be minutes. Min na siya. Okay, so we have 20,000 divided by 750 minutes. So our answer would be 26.67 units per minute. Okay, so we still do not get the desired unit because we still have to divide the kilogram. So 26.67 units per minute divided by kilogram is 0.37 units per kilogram per minute. Okay, so that is the dose of sodium, heparin sodium, that should be administered to the patient. Okay, so the desired unit again is amount. So you have units, and then the kilogram, and then the minute. So our final answer would be 0.37 units per kilogram per minute. So we have the dosage based on the creatinine clearance. Okay, so when we are going to talk about creatinine clearance, this is a measure of how well your kidney works. Okay, so I have here the kidney and the liver. These are major organs of elimination. So normally when we are going to administer our drug in our body, then it is normal for us to eliminate in a certain amount. Okay, it should be eliminated because when there will be no elimination happening in our system, then there will be accumulation of our drug in the system, and then it will lead to toxicity. So the two major organs of elimination is our kidney and our liver. So here on your left side, you will see a very good um, kidney. Okay, these are your nephrons, and then this one on your right, you will see a polycystic kidney disease, or not just a polycystic disease, but any other diseases. Okay, like for example, if you're old already, then your normal body function of your kidney is also decreased. Okay, on your lower pictures, you will see to your left, you will see here a good kidney. Okay, so if your kidney is good, then drugs will be able to filter through the glomerular filtration rate, and then it will undergo processes in the nephron, and then it will be once it will be filtered, then um, it is already eliminated in our body. Okay, it will go to the ureter and then the bladder, and then it will be excreted through the form of urine. Okay, so we have the term wipe. Okay, water soluble, ionic, polar polar form of our drugs are excreted. Okay, but some of the drugs are reabsorbed in our body. That's why it should be more polar to be able to excrete our drugs. Okay, so when there is an abnormal function of our kidney, then there will be lesser filtration, or it might not be able to filter our drugs, and then it will not be able to pass through the ureter and the bladder, and there will be no elimination that will happen. Okay, so what will happen? There will be an accumulation of our drugs in our body leading to toxicity. Okay, so ma-poison rata when there will be no effect of elimination in our kidney. So it is important again to eliminate the kidney, the not the kidney but the drugs in our body through the kidney or the liver. When we are going to talk about liver, there will be an enterohepatic recycling of the drugs, meaning to say when the drugs are pass through the kidney and not be able to pass through the filter, then it will go to the kidney for enterohepatic recycling, and then making it more polar, and then it will go back to the kidney again because it has become more polar, so it can already be eliminated. So creatinine clearance is a test that measures how well creatinine is removed from your body by your kidneys. This test gives better information than a blood creatinine test on how well your kidneys are working. The test is done both blood sample and the sample of urine collected over 24 hours. So when we talk about creatinine, it is a waste product that produced by muscles from the breakdown of the compound called creatine. Okay, creatinine is removed from the body by the kidneys, which filters almost all of it from blood and release it into the urine. This test measures the amount of creatinine in the blood and or the urine. Okay, so remember again, these are the your creatinine are the waste product from our muscles, okay, produced from our muscles, and then it should be filtered to our kidneys, and then there will be elimination that will happen. So it is important for us to measure the creatinine clearance of our patient, okay, to again measure if how well um, the kidneys are working. So you have here creatinine and creatinine clearance, serum creatinine. When we talk about serum creatinine, it is the creatinine in our blood. Okay, so the normal serum creatinine for men is zero point 0.8 to 1.8 milligrams per deciliter. For women, we have zero point 0.5 to 1.5 milligrams per deciliter. Increases with kidney malfunction. So there, if there is an increase of serum creatinine, then there will be a kidney malfunction that is happening. So urinary creatinine clearance normal value is 85 to 135 ml per minute. Requires a 24-hour urine specimen, decreases with renal malfunction. Okay, so ang creatinine clearance mo decrease siya with renal function. Nga naman siya mo decrease, but it cannot, remember, this is a urinary creatinine. Okay, so it decreases. It's because kung naatay kidney malfunction, dili siya maka-excrete through urine. So, ang ato ang creatinine, this is a measure of urinary creatinine, dili siya mapunta sa urine, therefore there is a decrease also of urinary creatinine clearance when there will be a renal malfunction. But for our serum creatinine, this is a measure of your creatinine in the blood. Okay, so if there is a kidney malfunction, then it will not pass through the kidney and it will accumulate in the blood. So there is an increase with kidney malfunction. So you have to read the diagnostic test to your right. Okay, so I give you a minute to you have to pause the video and read um, the paragraph. So to measure our creatinine clearance, we have this formula, Cockcroft-Gault formula, estimated creatinine clearance rate. Okay, this is a measure of your estimated creatinine clearance rate. So your Cockcroft and Gault are usually used to measure the creatinine clearance. Okay, it is also important in the board exam. So that's why you have to memorize the formulas. So creatinine clearance can be estimated using the serum creatinine levels. The Cockcroft-Gault or the CG formula uses a patient's weight in kilograms and a gender to predict creatinine clearance in milligrams per deciliter. The resulting creatinine clearance is multiplied by 0.85 if the patient is female to correct for the lower creatinine clearance in females. The CG or the Cockcroft and Gault formula is dependent on age and its main predictor for creatinine clearance. So below are the formula. So you have here Cockcroft and Gault for your male patient. So creatinine clearance in ml per minute. Remember that the units for our creatinine clearance is ml per minute. So you have there the 140 that is a standard value for our Cockcroft and Gault equation minus the age. So you have there times the weight of the patient or lean body weight of the patient in kilograms divided by the serum creatinine in milligrams per deciliter times 72. Okay, so that is how you are going to get the Cockcroft-Gault equation for male patient. So for our female patient, when you are going to use Cockcroft and Gault equation, it's just the same with our male. So you have remember again that the units is ml per minute. Okay, so 140 minus h times the weight of the patient in kilograms divided by serum creatinine in milligrams per deciliter times 72. And you have to multiply by 0.85 if female. Okay, so remember you have here the resulting creatinine clearance is multiplied by 0.85 if it is a female patient. Okay, but if male lang, wala lang multiplication of 0.85. Okay, so you have to memorize this and remember this formula for Cockcroft and Gault. So the creatinine clearance normal values are around 97 to 137 ml per minute in men, and then 88 to 128 ml per minute in women. So remember that the normal values for our creatinine clearance for women is lower compared to our male. Abnormal increases in creatinine clearance may be indicative of some kind of renal dysfunction, either filtration, existence of infection, reduced blood flow, dehydration of muscular problems. Okay, so again, it is important for us to measure the creatinine clearance. Next, you have the equation of Jellyfish equation. It does not require a patient's height or weight because it describes unstable renal function normalized to a body surface area of 1.73 meters square. It is now considered depreciated in favor of newer equation. So, kani si jellyfish, dili kaya ni siya stable measure of our creatinine clearance. That's why normally ang ginagamit is the Cockcroft and Gault equation. But we have to discuss this because you are going to learn how to compute this equation too. So for jellyfish, it's the same with Cockcroft and Gault. It should be um, uh, different from male and our female equation. For jellyfish, you have creatinine clearance in ml per minute is equal to 98 minus 0.8 times H minus 20. Okay, so you have here the H, the measure of H minus 20 divided by the serum creatinine. So you have to remember these formulas: 98 minus 0.8 times H minus 20 over serum creatinine. Okay, that is for male. For female patient, you have 98 minus 0.8 times H minus 20 times 0.9. Okay, if female divided by serum creatinine. So remember, it's just the same with male, but for female, you have to multiply by 0.9. Katong isa lahi pod niya siya i-multiply. Okay? So you have to remember this formula. So we will go on with the calculations already ha. Dapat we will learn how to calculate this and remember their formulas. Example calculation: determine the creatinine clearance rate for an 80-year-old male patient weighing 70 kilograms and having a serum creatinine of 2 milligrams, that is milligrams per deciliter. Use both the jellyfish and Cockcroft-Gault equation. First, you have jellyfish. So this is a male patient. Remember to identify the patient if it is a male or a female. If he or she is a male or a female. And then we have here jellyfish. Since we are looking for a male, we are going to use 98 minus 0.8 times H minus 20 divided by serum creatinine. Okay, so first you are going to um, replace the age. So we have 80 minus 20 times 98 times 0.8. Okay, first you have to get this 80 minus 20, we have 60, and then 98 times 0.8 times 60 divided by 2 milligrams per deciliter. Our answer would be 25 ml per minute. Okay, for our Cockcroft and Gault equation for male patient, we have creatinine clearance is equal to 140 minus H times the kilograms in the weight in kilograms divided by the serum creatinine times 72. So 140 minus the H times 70 So 140 minus 80, you have to get that first times the 70 divided by 72 times 2. So our answer would be 29.2 ml per minute. That is for Cockcroft and Gault equation. Remember that you have to always get the uh, two decimal places, okay? So you have to round it off to two decimal places. Pero kani ako wala lang ako siya round off, but for you, you have to round it off to two decimal places. But if your answer is a whole number, then you don't need to um, convert that to two decimal places. All you have to do is to write the whole number. But if it is a decimal and it is more than 3, then you have to round it off to two decimal places. Another example, we have a 70-year-old gentleman and his wife, who is 60-year-old, have the annual checkup. He weigh 160 pounds and she 126 pounds. His blood work revealed a serum creatinine of 1.3 milligram per deciliter, and hers is 1.1 milligrams per deciliter. Using Cockcroft and Gault equation, calculate the respective creatinine clearance rates. Okay, so we have here a male patient, and then we also have a female patient. Okay, wife. So you have here a male and a female. But what is the formula that you will be using? We have Cockcroft and Gault equation. So we have to write the formula for our male patient. So 140 minus age times the weight in kilograms divided by the serum creatinine in milligrams per deciliter times 72. Replace the value. So we have 140 minus 70 times 72.7, because you have to convert the pounds to kilograms, because we have to get kilograms. So the conversion there is 72.7 kilograms. Okay, divided by 72 times 1.3 milligrams per deciliter. So our answer here would be 54.37 ml per minute. That is for the creatinine clearance for our male patient. For our female patient, we have to again um, use the same formula, but you have to multiply by 0.85 if it is a female. So 140 minus age times the weight in kilograms divided by the serum creatinine in milligrams per deciliter times 72 times 0.85 if female. Replace the value, so we have 140 minus 68 times 57.27. Why 57.27? We have to convert 126 pounds to kilograms, divided by 72 times the serum creatinine, which is 1.1 milligrams per deciliter, and times 0.85, which is the standard formula for our female Cockcroft and Gault equation. So our answer for our female patient's creatinine clearance would be 44.25 ml per minute. Okay, ml per minute half for our units. So now we're done with our creatinine clearance, those calculations. So we are going to talk about isotonic solutions. So isotonic solutions is important, especially our body will absorb only those that are isotonic. Okay, so isotonic solution is one that has the same osmolarity or the solute concentration as another solution. If these two solutions are separated by a semi-permeable, water will flow equal parts of each of the solution into the other. Okay, so this is how your isotonic solution um, looks like. So you have there the solute molecules and the water molecules. So remember that there is no osmotic flow. So if a cell is placed in an isotonic solution, there will be no net flow of water into or out of the cell, and the cell's volume will remain stable. Okay, so that's why we have to identify the type of solution. So we have here hypertonic, isotonic, and hypotonic blood cells. So examples of isotonic solutions, we for our blood cells, we have hypertonic, isotonic, and hypotonic. Remember, for hypertonic, there is a a release of our water from our red blood cells. Okay, so muna siya, it causes the red blood cells to shrink. Okay, and then for isotonic solution, there is an equal in of our water and out of our water from the RBC. So stable ra ang ato ang red blood cells. Wala rin nahitabo niya. Okay? So equal raman ang pag-in and out sa water. But when we are going to talk about hypotonic, there is um there is that increase of water in our red blood cell causing it to burst. Okay? So kung sobraan na po ng water ang ato ang atong red blood cells, then it will cause our red blood cells to burst. But kung gamay ra po kay water kay sige na siya og pagawas, then it will shrink. Okay, so when the blood plasma surrounds blood cells in an isotonic solution compared to the solution inside the blood cells, the cells will function normally. So the isotonic solution allows the cells to move water and nutrients in and out of the cells. So that is the importance of our isotonic solution. It again it allows the cells to move water and nutrients in and out of the cells. So that is a normal that is a normal solution of our red blood cells. This is necessary for blood cells to perform their function of delivering oxygen and other nutrients to our parts of the body. If the cells are in an hypertonic environment, they will be plasmolyzed and will not contain enough water to perform cellular functions. It's because iyang gi-release tanan ang water. If the cells exist in a hypotonic environment, they will lyse, spilling their contents into the bloodstream. Okay, so malanay ra siya or ma-burst. That these can cause dangerous side effects as well as the loss of many blood cells. So these events can be seen in the no, we don't have a graph. I did not include the graph, so we have to delete that. So you have here a hypotonic. So what is a hypotonic? When a solution has comparatively more water and less solute. Okay? So mas dagan ang water mo adto sa atong red blood cells and gamay ra kayo ang solute, then there is an increase of water or the solvents in our red blood cells causing it to burst. So hypertonic, a solution with less water, more solute than another solution. Okay? So muna iyang ipagawas ang water, then there is a shrink of our red blood cells. So isosmotic is a solution that have the same osmotic pressure. Okay, and then isotonic, the solution that have the same osmotic pressure as a specific body fluid or equal tone. So when we are talking about a solution that have the same osmotic, we are calling that as isosmotic. But if we are going to relate it with our body, then we are going to talk about isotonic solution because we are talking about other fluids in our body system. Okay, so what is a diffusion? A diffusion is a movement of molecules from high concentration to low concentration. Okay, so if this is letter A and B, then remember that diffusion is a movement of molecules from high concentration to low. So if this is your molecules, then um, it will be transferred to low molecules of concentration to your B. And when we talk about osmosis, we have movement of solvent water across the semi-permeable membrane through high to low solvent concentration. This time we are talking about solvent. So your solvent there is water and high to low. So if this is a higher, um, this one has a higher solvent concentration while this one has low solvent concentration because it has more solute on it. So we have it has to pass through a semi-permeable membrane and then it will transport only the solvent or the water molecules to the ones that have a less solvent concentration. So this will what it looks like. Okay, so maana ni siya. So magamay ang iyang solvent and then mapunta siya sa B. Okay? Para iyang i-equilibrate ang solvent and the solute concentration. Wala siya ang osmosis. So we have to talk about dissociation. So what is a dissociation? There is a separation of molecules or ionic compounds or the cation or anion into smaller parts. This usually happens when ionic compounds are placed in water. Okay, so kanang mga compounds with charges, they can be separated through dissociation when they are placed with water. Okay, remember that our water is a polar um, it is a polar molecule that has a positive and a negative on it. So um, we have to, this is an amphoteric, so it can be an acid or amphoteric. Wait ha, Okay, so when we talk about amphoteric, we are talking that a water can act as a base or an acid, okay? But since our water is a polar molecule, and if we are going to add sodium chloride, this is a sodium chloride, okay, or your table salt. So you have there cation and an ion. So when we're talking about dissociation, there is a separation of these two molecules. Okay, so ang sodium must separate to the chloride. Okay, so if we're going to add water in it, we have the positive and the negative charges of our water. Then if the you remember that opposites attract. Okay, so when there is an interaction between these molecules and our water, then the positive molecules of our water will be attracted to the negative form or the anion of our sodium chloride, and then the negative of our water will be attracted to the sodium of or the anion the cation of our sodium chloride. Okay, so remember that opposites attract. When salt is put into water, the water molecules pull apart the sodium and the chloride ions, making them separated. Okay, so when there is a attraction of the negative and a positive from our water and our compound, then there will be a separation or dissociation that will happen. So it is important for us to calculate also the dissociation. Okay, so we have to know the calculations of the dissociation. Remember that when we're talking about liquid solutions, then um, it must flow kana ganing 'di ba mo flow ra siya kanang easily flow, so our molecules will move around easily. Okay, that's why pwede siya ma-attract diretso sa atong negative and the positive to negative. So you have here the separation of the cation and an ion with a ionic compound is placed in water. Okay, so if your positive or the cation is attracted to your anion in water, and then the anion is attracted to the cation in water. So when is put in water, water molecules pull apart the sodium and the chloride ion. So this is now what is happening here is there is a separation of sodium and our chloride with water. Okay, before and after. So if this is your equation, if you are going to look at the dissociation of our sodium chloride upon the addition of our water, then this is what happens. Okay, so when we are going to talk about aqueous, so if a solute or the salt is dissolving in water solvent, then we have to call this an aqueous solution. Okay, so if this is your reactant, then this side is your reactant and this side is your product, then there will be a dissociation that is happening. Okay, so this is not the normal function of our um, reactant and our product, because we are only getting here the dissociation factor. Okay, so when we are talking about aqueous, if the solute is added to a water, we are talking about aqueous solution. But when we're talking about water only, then it is a liquid in nature. Okay, so sodium chloride upon the addition of water, or it becomes a salt in water, then if there will be dissociation that is happening, there is a separation of our cation and an ion. Okay, so sodium plus your chloride. So this is the dissociation. So our um, most of our compounds are divided into strong electrolytes and weak electrolytes depending on how strong the charges are, or how strong it will dissociate. Okay, because if you're talking about strong electrolytes, we are going to talk about strong acids and strong bases. Okay, when these two come together, there will be a separation of our positive and our negative charges, okay, making the light bulb light. Okay, so kung strong ang inyong electrolytes, there will be um, a conduction of electricity that is happening. Okay, so that's why you can determine if the your uh, your solution is a strong electrolyte or a weak electrolyte depending on the dissociation. Okay, so kung strong electrolytes, mas mo dissociate siya 100%, there is 100% dissociation. Okay, so it is what we call a strong electrolyte. But if you're going to talk about weak electrolytes, we are talking here of weak acids and weak bases. So there is a partial dissociation of electrolytes in our water. So gamay lang kayang iyang ilight sa bulb, or um, there is a less conduction of our electricity in our solution. Okay, so dili siya tanan ma-dissociate or ma-separate into positive and negative. So we are going to consider this as weak electrolytes. So this is how we are going to compute for our dissociation factor. We are going to use the Van 't Hoff factor. It has a symbol of I. Okay, remember that for our non-electrolyte, since this is a constant electrolyte, we have to use 1 for our Van 't Hoff factor. That is the constant value for our non-electrolytes. Remember, if we are going to talk about non-electrolytes or a weak electrolytes, then it should be dissociated lesser in our water. That's why we have to have this value, okay, of 1. So non-electrolytes, like for example, you have your sugar, or the chemical formula, we have C6H12O6, we have 1. Okay, non-electrolytes. But for our electrolytes, remember that these can be dissociated, okay, into positive and negative ion charges. So we can measure here the dissociation factor. Okay, for example, you have your sodium chloride. Okay, so let's go back here for our non-electrolytes, substance that do not yield ions when dissolved in water are called non-electrolytes. Okay, this does not yield an ion. So for example, you have your NH3 or your ammonia, your sugar, your carbon dioxide, and your oxygen. So it has a 1 Van 't Hoff factor or dissociation factor. For our electrolytes, substances that yield ions when dissolved in water are called electrolytes. So we have here sodium chloride or your table salt. You have sodium. This can be dissociated into sodium and chloride ions. So we have two. You have here sodium and then chloride. So we have two Van 't Hoff factor. This one you have CaCl2. So you have here two chloride. So we have Ca plus the charge 2 positive plus 2 Cl. So 1 here, 1 red in here, and then you have here 2. So 1 plus 2 is 3 ion. So on your left, you will see here the magnesium chloride. So magnesium, positive 2 plus 2 Cl. So remember that um, the coefficient would be 2 and then 1 for magnesium. So 1 plus 2, we have 3. And then here you have AlCl3. So you have here 1 and then you have 3. Okay, so 1 plus 3 is 4. And then you also have here AlSO4 3. So you have here 3 plus 2, you have 5, or the Van 't Hoff factor of AlSO4 is 5. Okay, so that is how you are going to look at the dissociation factor. So the standard ionic value we have 9.09 grams of sodium chloride in 1000 gram of water should make a solution isotonic. So here I will let you see the standard isotonic value of our um, solution in our system. Okay, remember that we have 9.09 gram of sodium chloride in 1000 gram of water. It should make a solution isotonic. Okay, so the standard percentage of our isotonic solution is 0.9. Okay, mauna jud na siya ang ato ang standard, so 0.9%, but this is a standard formula already. Okay, so ako lang ipakita niyo kung nganong nakuha na to ang 0.9. So, we have here 1.86 degrees Celsius times our 1.8, the dissociation factor, over 0.52 degrees Celsius is equal to 58.5 for the molecular weight of our sodium chloride times X. Okay, so we have to get this, we have 9.09 grams. Okay, so kani siya given na siya, kani siya tanan na formula given na siya. Okay, this is how we are going to get the isotonic value of our sodium chloride. Okay, di ba? Importante man na naatay salt sa ato ang body. So we have here 9.09 grams of 1000 grams times 100%. We will get a 0.9%. Okay, so this is how you are going to apply the simple isotonic solution. So 0.52 times the molecular weight over 1.86 and the dissociation factor. So you have there the grams of solute per 1000 grams of solution. So kani mo na siya ang inyo ang um, yun sa niyo siya pagkuha. Okay? So, kato siya, dili lang to siya importante na inyo ang i-memorize ang formula, but you have to remember that we have 0.9% isotonic solution. So we have here the calculation of the Van 't Hoff factor or the dissociation factor. So zinc sulfate is a 2-ion electrolyte dissociating at 40% in a certain concentration. Calculate its dissociation factor. So you have here a zinc sulfate, which is a 2-ion electrolyte. So it can be separated to zinc and the sulfate. Okay, so zinc and sulfate, and the dissociation factor is, the dissociating percentage is 40%. So you have to distribute the 40%, so still 40% and then 40%. Okay, kay the same raman siya na compound. Okay, so 40 and 40 is equal to this one, 40 din he, if we are talking about 100%. Okay, so 40 lang na siya. But if you are going to measure the particles, you have to distribute the 40 both elements. So you have zinc and the sulfate. So the undissociated, you can already determine the undissociated katong wala na dissociate or na separate to two ions. Okay, so you have 60% ang iyang dissociation. Okay, kaya ang iya ramang gisulti din is 40, that 40% ang dissociation. So we have 40 minus, or 100 minus 40 is 60. That is the undissociated. So 40 plus 40 is 80, plus 60, we have 140 for our particles. And then 40 for our percentage, we have 40 plus 60, we have 100%. Okay, so to get the Van 't Hoff factor, we have to write the 140 particles in the numerator divided by 100. So 140 divided by 100 is 1.4. So this will be your answer, or your Van 't Hoff factor for our zinc sulfate. Okay, so again, you have to distribute 40% both our zinc and our sulfate if you're going to get the particles. And then for our percentage, we only have to use the 40%. Okay, and then we can already identify the undissociated value, which is 60%, through 100% minus 40% is 60%, that is undissociated. So you also have to write 60% undissociated. This is undissociated. Okay, undissociated. So that is 140 particles. 140 divided by 100 is 1.4. dissociation factor. Next, we have here, if the dissociation is not stated, assume that we have 80% dissociation constant. Okay, so kung ang problem na to wala nag-talk about percent dissociation, then we are going to assume it is 80%. Okay? So, remember that mo na siya ang inyo sa board exam. Okay? Kung mo gawas ni siya nga question sa board exam, then wala siya ni talk about dissociation percentage. So, we have to assume that it is 80% dissociation constant. Okay? So, calculate the dissociation factor of our sodium chloride. Okay, by the way, kani siya mga I factor or the Van Hoff factor and the dissociation factor is already given. Okay, kani gipakita lang sa inyo kung giun sa pagkuha ang ato ang Van Hoff factor or the I factor. Okay, so you have here calculate the dissociation factor of our sodium chloride. So remember that we have two ion here. You have sodium and our chloride. This is a positive and a negative charge. So we have to separate the sodium and chloride. And we are going to assume that it is 80%. So if we are going to get the percentage, we are going to use only 80%. But if we are talking about the particles, we have to distribute 80% both. Okay, so sodium and our chloride. And remember, this is undissociated. So this should be undissociated. Dili na siya dissociated lang. This is undissociated. So, 100 minus 80, we have 20% undissociation. Okay, so 80 plus 80 plus 20, we have 180 particles. So, if to get the Van Hoff factor, we have to divide the particles by 100%. So, 180 divided by 100 is 1.8 dissociation factor for our sodium chloride. So another, we have zinc chloride is a 3-ion electrolyte dissociating at 80% in a certain concentration. Calculate the dissociation factor of our zinc. This is not sodium chloride, this is zinc chloride. Okay? Zinc chloride na siya. So, 3-ion man siya, so it can dissociate into zinc and the chloride and chloride because we have to dissociate two chlorides. So, since 80% ang iyang dissociation percentage, then we have to distribute into each elements. So zinc 80, chloride 80, and then 80. So if we are going to get the percentage, we are going to use only the 80% because 100 naman taman. But if we are going to talk about the particles, we have to distribute each. Okay, and this time this one is undissociated. Okay, so you can compute for the undissociation percentage by 100 minus 80, we have 20% undissociated. So 80 plus 80 plus 80 plus 20, we have 260 particles. To get the Van Hoff factor, we have to divide the 260 over 100. So our answer would be 2.6 dissociation factor for our zinc chloride. Okay, so that is how you're going to get the dissociation factor. So now we are going to talk about the equivalent values. Okay, so in connection with our isotonic values, in our system, we have to get also the equivalent value to make the solution isotonic. So E value is one of the most underrated calculation. First step is to memorize the equation. You have this equation, you have to at least read na lang this one and then familiarize. So to understand each value, it's really not too difficult because there is only two variables that changes, and it is the Van Hoff factor or the dissociation factor and the molecular weight, and all the other formulas remain constant. For remember, if we have the one ion or the non-electrolyte, we have the Van Hoff factor of I or the dissociation factor of 1. Okay, so we have here 2 ion dissociation, so we have 1.8, 3, 2.64, 3.4, and 5, 4.2. Okay, so you have to remember the Van Hoff factor or the dissociation factor if your ion is 1, 2, 3, 4, or 5 respectively. Okay, so you have next step is to understand what they actually means. The value provides above the dissociation ions. So when we say about one ion, then it is equal to 1. This means that one ion will be dissociate into one particle. two ions dissociate into 1.8 particles. So let's say that a drug molecular weight is 150 with an ion factor or dissociation factor of 4. What is the equivalent value of a drug? So since this is a 4 ion dissociation, so we have this one, 3.4. So 58, to get the equivalent, we have this standard value, 58.5 times the um, ion or the Van factor for our substance divided by the molecular weight of our substance. That's the the dissociation factor for our sodium. Okay, so you have to multiply the numerators and the denominator, so you will get the equivalent value of 0.737 or 0.74. Okay, so that is the equivalent value. But later on, after this slide, we will proceed with the e-value still. Okay, so para mas masabtan ninyo ang computation of our e-value. Okay, so kani siya is just a summary of the e-value. So in computing for the e-value or the equivalent value for a substance, we have to use the formula. Okay, di ba ganiha, gidrit siya raman niya. So we have to use, since we are going to talk about um, sodium most of the time, so we have to get the molecular weight of our sodium chloride. Mo to siya ang 58.5 ba to? Muna siya standard na ng uban na values. So we have here the molecular weight of our sodium chloride and the dissociation factor of our sodium chloride times the Van 't Hoff factor or the dissociation factor of our substance. So remember ganihan niingon siya nga ang mag-change ra gyud ana is the dissociation factor of our substance and the molecular weight of our substance, but all the others are constant for our sodium chloride. Okay, so this is the formula. We have molecular weight of sodium chloride over the dissociation factor of sodium chloride times the dissociation factor of the substance over the molecular weight of the substance. So that is how we are going to get the sodium chloride equivalent. This is important because we have to again get the sodium chloride equivalent because it should be isotonic. The solution should be isotonic to be able to um, function well. Okay, so you have here the first problem, 1 gram of atropine sulfate in 1000 ml solution. So the molecular weight of your sodium chloride is already the standard. We have 58.5 and the Van 't Hoff factor or the dissociation factor is 1.8, while the molecular weight of our atropine is 695 and the Van 't Hoff factor would be 2.6. Okay, so you have to write the formula and replace the values. Okay, so you have 58.5 for the molecular weight of our sodium chloride and the Van 't Hoff factor for our sodium chloride, which is 1.8 times 2.6, the Van 't Hoff factor of our substance, divided by 695, the molecular weight of our substance. So you have to get the numerators, the product of our numerators and our denominators. So you have 152.1 over 1251. Okay, so since we are going to get we are given here a gram of our atropine, so we have to find also this one. Okay, so since you know that the molecular weight of our atropine is in the denominator, so you have to write 1 gram in the denominator also. Okay, so what is left is we have this one. Okay, so kani atong gipangita. So cross multiply, since you have equal sign in the center, so you have to cross multiply. So 152.1 times 1 gram divided by 1251. Okay, so you have here 1251 question mark. Okay, so to cancel the values before your question mark, you have to divide both in the denominator. So what you're going to do on your right side, you're going to do on your left side. So muna siya 1251 sa right, and then you have to also write 1251 sa left. Okay, so what is left is the question mark. So you can have the formula already. So you have this one. By the way, you should not cancel this one ha. Kay kanilang inyong i-cancel kay maura man na siya ang naay 1251 and 1251. So 152.1 times 1 gram divided by 1251. So our answer would be 0.12. Okay, that is the E value for our atropine. So that is the equivalent sodium chloride equivalent for our atropine, that is 0.12 if you are given a gram. Okay, and then how much atropine is added. If you're asked if how much the atropine is added to make a solution isotonic, then you have to make the isotonic to make the solution isotonic, you have to convert this, you have to subtract by 0.9. Remember ganiha sa pinakauna na slides nato sa ato ang isotonic solution, I've let you compute sa isotonic value of our sodium chloride. So we have here 0.9. Remember that we have a 0.9 sodium chloride equivalent. Okay, so we have 0.9, that is a standard already. So you have to subtract the E value for our atropine. Okay, so you have 0.12. The E value for our atropine is 0.78. That is the atropine that must be added to make the isotonic to make an isotonic solution. If you are asked how much atropine is added. Okay, but kung wala ra siya nag-ask of how much atropine is added, then this will be your answer. Pero kay ni-ask man siya, then your answer would be 0.78. Okay, so you have to subtract 0.9 minus 0.12. Next, we have here papaverine hydrochloride has a molecular weight of 376, is a 2-ion electrolyte dissociating at 80% in a given concentration. Calculate its chloride equivalent given an ionic factor of 1.8. Okay, so you have here, this is how you're going to get the E value for our papaverine hydrochloride. Okay, so you have to write the formula, the 58.5 over 1.8 times the I of our substance and then the molecular weight of our substance. So you have to calculate the numerator and the denominator. You have 105.3 over 673.8. So our answer would be 0.16. So that is the E value for our papaverine hydrochloride. That is the sodium chloride equivalent for our substance. Next, we have calculate the sodium chloride equivalent for glycerin, a non-electrolyte. Remember, this is non-electrolyte with a molecular weight of 92 and an I factor of 1.0. Okay, so since it is a non-electrolyte, we assume that we have one, one is the value for our Van Til factor. So you have to write the formula 58.5 over 1.8 times 1.0 divided by the 92 for our molecular weight. And then get the products of our numerator and the denominator. So 85.5 over 165.6 is 0.35. That is the sodium chloride equivalent value for our glycerin. So here we are going to talk about the parenterals and ophthalmic preparations isotonic solution. Okay, so isotonic solution is a solution having the same osmotic pressure as a body fluid. Ophthalmic, nasal, and parenteral solution must be isotonic. Okay, so it is important nga kanang atong mga gipang drop sa atong eyes should be isotonic to be able to pass through our mga system nato sa ato ang body. Okay, so hypotonic solution, you know that already, and a hypertonic solution, you know that already. So pause the video if you want to read the definition. So this time we have different steps, or we have to follow these steps to get the isotonic value for our ophthalmic and our parenteral solution to make this isotonic. Okay, so first you have to calculate the amount in grams. Step 1, you have here calculate the amount in grams of sodium chloride represented by the ingredients in the prescription. Multiply the amount in grams of each substance by its sodium chloride equivalent, either from the tables or by calculation. So you already have the standard value there. So for step 2, Letter B, you have here calculate the amount in grams of sodium chloride alone that would be contained in the isotonic solution of the total volume specified in the prescription. So step 3, you have there letter C, subtract the amount of sodium chloride represented by the ingredients in the prescription, that is your step 1, from the amount of our sodium chloride needed to prepare the isotonic solution, that is step 2. So you have here step 2 minus step 1. And then step 4, we have here if the agent other than sodium chloride such as boric acid, dextrose, sodium or potassium nitrate is to be used to make the solution isotonic, divide the amount. Okay, so in the next slide, you will see how we are going to compute the isotonic solutions. So you have here how many milligram of boric acid should be used in compounding the following prescription. Proparacaine HCl is equal to 0.5%, pilocarpine HCl is 2%, then the boric acid is the sufficient quantity or the QS only. So purified water is equal to 60 ml. So make isotonic acid solution and the seek is 1 drop each eye. So step 1, remember step 1, to calculate the amount of sodium chloride represented by each ingredient in a prescription by multiplying the amount of each ingredient by its sodium chloride equivalent. For our proparacaine hydrochloride, since we have proparacaine and pilocarpine HCl, we have to get the salt equivalent or the sodium chloride equivalent of these two. Okay, your HCl there is the salt, so that's why you have to get first the sodium chloride equivalent of these two. So the sodium chloride equivalent for this is 0.15. So remember that we have here 0.5 grams over 100 na siya, 100 ml. Okay, so from here you have to get 0.5 over 100, diba? You can separate this by 0.5 to 100. Okay, since percentage man siya, it can be weight per volume. Okay, the concentration can be weight per volume. So, it should be 0.5 over 100. Okay, so the percent can be separated to 0.5 grams over 100 ml in weight per volume. Since you are given there 1,000 you have to by the way you have to um, make this into milligrams, so we have to convert 0.5 grams to milligrams by converting it by multiplying it to 1000 milligrams. Cancel out the grams and then you have there 60, which is your water, so you have there milligrams per ml. Okay, so this is milligrams per ml. So you have there 60, 1000, you have there 0.5 times 1000 milligrams divided by 1000 times 60. I know 0.5 times 1000 divided by 100 ml times 60, we have 3000 milligrams per 100 ml. Okay, so what we are going to do here is to multiply with the sodium chloride equivalent of our proparacaine hydrochloride, which is 0.15. So our answer would be 45 milligrams of sodium chloride equivalent. Okay, so for our pilocarpine, we have 2 grams. Okay, so we can convert this percentage into weight per volume concentration. So 2 grams over 100 ml. So we have to make this to milligrams. So we have to convert grams to ml. So you have 2 times 1000 milligrams. And then you have to multiply it by the water. Okay. So we have here 2 times 1000 times 60 over 100, so we have 120,000 milligrams per 100 times the E value for our pilocarpine HCl, which is 0.24. Okay, 0.24. So our answer would be 288 milligrams. That is for our sodium chloride equivalent. So now we have to compute the sodium chloride equivalent of these two. So 45 milligrams plus 288 milligrams is equal to 333 milligrams of NaCl represented. Okay? If you are given two salts here. Pero kung isa lang, ang isa lang inyong kuha sodium chloride equivalent. So step 2, you have here 0.9 grams over 100 ml times 1000 grams. So you have here, 'di ba? Calculate the amount of sodium chloride alone that would be contained in an isotonic solution of the volume specified in the prescription, namely the amount of sodium chloride in 0.9% solution of the specified volume. So for our step 2, you have here 0.9 grams over 100 ml times 1000 milligrams because you have to convert grams to our milligrams. Okay, so you have to multiply by 1000 milligrams. Okay, so times 60 ml is equal to 540 milligrams. So this is um, the milligram of sodium chloride in 60 ml of isotonic solution. Okay, so you know already that we have the standard value for our sodium chloride, but we have to get the sodium chloride of depending on the amount of our solvent. Okay, so you have zero point 0.9. Your 0.9% can be written as zero point 0.9 grams per 100 ml in weight per volume concentration. But since we are going to get the milligrams, so you have to cancel out the grams and convert grams to milligrams. So you have to also multiply the amount of our solvent. So you have 60 ml. So zero point 0.9 times 1000 milligrams over 100 ml times 60, we have 540 milligrams. That is a milligram of sodium chloride in 60 ml of isotonic sodium chloride solution. Step 3, we have to subtract the amount of sodium chloride represented by the ingredient in the prescription, which is the step 1, from the amount of our sodium chloride alone that would be represented in the specific volume of isotonic solution. Okay, so for step 2, we have here 540 milligrams minus 333 milligrams. For step 1, we have 207 milligrams. So this is a milligram of NaCl required to make the solution isotonic. So for step 3, you have 540 milligrams. That is for step 2 minus 333 milligrams. That is from your step 1. So we have 207 milligrams. So that is again for your step 3. Because for step 3, you have to subtract step 2 minus step 1. And then for step 4, since you already have a value for your step 3, we have to divide by the E value of our boric acid, diba? Boric acid man ato ang solution ganiha sa problem, diba? So, you have to get the E value. Pero, gihatag na siya, okay? You know already how to compute for the E value. It is 0.52 for our boric acid. So, 207 milligrams divided by 0.52 is 398.08 milligram boric acid to be used. So this is the summary. So you have here from your problem, you have how many milligrams of boric acid should be used in compounding the following prescription. So you are given the ingredients to make a milligram of boric acid. Okay, so step 1, you have to get again. For step 1, you have to calculate the amount of sodium chloride represented by each ingredients. So since you have proparacaine and pilocarpine, you have to get the sodium chloride equivalent by multiplying it to their sodium chloride equivalent. Okay? So this is the summary. You have to, if malibog mo, then you just follow the steps dito and then you have to analyze kung giunsa na siya pagkuha. Okay? Step we have another problem here. So you have how many milligrams of potassium nitrate should be used in compounding the following prescription isotonic. So you have a solution of silver nitrate, which is 60 ml and 1 is to 500 in the concentration of weight per volume. Okay, for step 1, you have 1 gram over 500 ml. Okay, kay naa kay concentration diri of 1 is to 500. So you can write it as 1 gram over 500 ml because your concentration is in weight per volume, because you are going to convert this to a you're going to convert this into a milligram, so you have to multiply by 1000, and then your you have here an ml, so you have this. So 1 gram times 1000 milligram over 500 ml times 1 gram, cancel out the grams, times 60 ml is equal to 120 milligram times 0.33. Your 0.33 there is the E value, equivalent value of your silver nitrate. Okay? Silver nitrate ba? Wait. Yes, that is for your silver nitrate. Okay, so that is the E value for your silver nitrate. So your answer would be 39.6 milligrams of sodium chloride represented. Muna siya sa step 1. But for your step 2, remember ha, ang step 2 ninyo, same ra gyud na siya tanan. O how giunsa ninyo siya pag-process. So you have to memorize na lang the step 2. Okay, what matters there is kani ang 60 ml. Okay, what if ang gibutang dinhi is 70 ml? Okay, so you also have to write 70 here. Same here. Okay, mo matter na siya. Then kung what if 80% ang gibutang dinhi or 90% ba? So you also have to change if this is 80% or 90%. Okay, so since 60 ml raman siya, so we have to multiply it by 60 ml. So cancel out the grams. So 0.9, okay? Okay, remember step 2, you have your calculate the amount of sodium chloride alone that would be contained in the isotonic solution of the volume specified in the prescription. So sodium chloride alone raman siya. Remember that you already have your value for your sodium chloride, which is 0.9%, diba? 0.9% can be written as 0.9 gram over 100 ml. 'Di ba? Mo na siyang isotonic value sa ato ang sodium chloride. So you can write that as 0.9 grams per 100 ml in weight per volume. So you have to get the milligram equivalent. So you have to convert this to milligrams. So grams to milligrams and multiply it by the kaning solvent niya. So we have times 60 is equal to 540 milligrams. So step 3, you have step 2 minus step 1 equals your step 3. So 540 milligrams over minus 39.6 milligrams is equal to 500.4 milligrams. And then step 4, you have to divide step 3 by its E value. Okay, so you have 0.58 for your potassium nitrate. Okay, that is the E value for your potassium nitrate. Kani siya E value ni siya sa inyong silver nitrate. Okay, so mo ni siya ang gigamit. Silver nitrate. Silver nitrate man ni siya, 'di ba? So you have to multiply it by the E value. But this time you have to divide step 3 by its E volume of the potassium nitrate. Kay mo man ni siya ang inyo ang final product. Okay, so your answer would be 862.76 milligrams. So that is for your potassium nitrate to be used. That is your potassium nitrate to be used to make the solution isotonic. So that ends our discussion. So I hope you've learned something, and please watch this video. Thank you so much, everyone.